Hey AP Physics students, I'm going to give you some notes here about reading a potential energy curve. There's really not a whole lot to say. These should be pretty short and sweet. Definitely no free pizza here. I'm going to give you a couple examples here. I think I've also alluded to the relationships that we're going to talk about here in some other notes or homework problems, perhaps. So this is just a real concise spot for us to make sure we understand that. Here's a couple of things that we know. If we were going to look at, for example, a spring, we know that spring potential energy is equal to 1/2 kx squared, where x is the displacement of the spring from equilibrium. Equilibrium, of course, just means no stretchy or pulley. So what does that look like? What if we were going to make a graph of potential energy versus position? What would that look like? Well, it's just a parabola, right? I mean, it's it's like y equals this x squared. So we know about graphs like that. So it would look like well, it looks awfully like a straight line, doesn't it? Sorry. So I'm kind of zoomed in on this parabola. Anyway, you just take my word for it. Use your imagination. That's a parabola. So it would look like that. Now, one of the well, I think this is kind of cool. I guess I just think physics is cool, but one of the cool things about these potential energy curves is you can almost understand like what an object is going to do. Potential energies are associated with forces. So what is going to happen if, you took some object and you put it at this location, at this x position? What would it do? Well, if it was here, I mean, we know about springs, right? The spring force is going to be this way on it. It's going to pull it back to here, and then as soon as it passes the equilibrium, it'll keep going this way, but the spring force will be this way, so the velocity will be this way, acceleration, net force will be this way, so it'll start slowing down, and then oscillate back and forth on a spring. One nice visual here is you could imagine if you were putting something here, imagine that thing was like here, like kind of resting on the graph, like on a little skateboard, or maybe it's like a little ball or something like that. And what happens when you release it? It's going to roll down this way. It's going to roll back. So it kind of behaves almost as if it's on the curve, as if the curve was some kind of physical structure. And not only that, but so here, like if you put it here, of course it's going to slide this way because that's the downward slope here. So the direction of the force on this is the direction that it would roll here, but more specifically, the derivative of your potential energy curve here is equal to kx. And of course, spring force is equal to negative kx. So this is the opposite of that spring force. And how about something else? How about some other conservative force that has a potential energy? Gravity on our planet. We know that the potential energy we assign to that, our mathematical model, is this. And h is the position variable here. So what if we made a graph of that? What would that look like? Potential energy versus position. You could say x and the heights. I think it makes more sense to me to call that h, where that variable height is our position. Now, you could have negative heights, right? I mean, it doesn't, because, if you said, let's let the edge of this lab table that I'm working at right now, let's let that be height 0. Well, something could go below that, and then you'd end up with a negative value for this. It's really the change in that quantity that matters. So I feel okay about doing that. Now, what about this little like skateboard or steel ball analogy? What happens here? So if you put that here, what happens? Well, it goes this way, right? And it keeps getting faster and faster and faster. Just like an object, if you release it at height h, it will fall, its height will decrease, it will accelerate in that direction. So how about the derivative with respect to position? I guess I could say dh. I just really want to say dx here because I'm more consistent with what we're going to say in a second in general. So this is my position variable. This is just like a constant times that. So like as if this was some number times this to the first power. So the derivative of that is just mg. And of course that's the opposite of gravitational force. Because gravitational force, if we're paying attention to direction and height is positive and negative, then this would be negative mg. So in general, the derivative of a potential energy function that's given as a function of position is equal to the opposite of the force associated with that potential energy. Cool. So that's the thing, and of course if you know force, then you can get to acceleration, you can figure out other stuff too. And I think that is all I'm going to say here. There's a couple problems from the book, and this might be one of those assignments where you really need to work through the first problem with me and then take over yourself after that. We'll see how it goes. All right, that's it. 7 minutes or less.